Let's talk about where this goes next now that we have an understanding of what implicit differentiation looks like. And I mentioned earlier, we're going to be able to apply this to some of our geometric formulas. So I want to reintroduce you to one of your formulas from geometry. Let's consider the formula for the volume of a sphere. And in case you don't remember from the couple of years that have passed since you took geometry, the volume of a sphere is expressed as the volume equals 4/3 pi r cubed. And this formula related the volume of a sphere to its radius. It ends up being cubed. That's why we get 3 dimensions to volume and things like that. So hopefully you have a pretty good understanding of how this formula works and some of the things that are going on there. Well, one of the things we're going to be really interested in fact, we're going to have an entire discussion on this in Unit 4, is this idea that we can actually differentiate both sides of this equation. And it's worth noting here that the volume is expressed as a function of the radius here, which is how we kind of understand the volume of a sphere. But through this process called implicit differentiation, we're going to be able to differentiate both sides of that equation with respect to any variable that we want. And so let's do this with respect to time. And I'm going to go ahead and do this for you. We'll have a lesson in Unit 4 that really focuses on this skill, but we've got the pieces there to do that. If I take the derivative of both sides of this equation with respect to time, the derivative of volume with respect to time is going to be the derivative of volume, or v, with respect to v, which is just 1 times dv dt. So that's what I would get on the left side. If I take the derivative of this right side with respect to time, I'll take the derivative with respect to r. So the derivative of 4/3 pi r cubed. Remember, 4/3 pi is all a constant value. So if I take the derivative of this function with respect to r, I'll multiply the 3 times 4/3 pi. The 3's would cancel and you get 4 pi. Reduce the power of the radius by 1. So there's the derivative with respect to r times the derivative of the radius with respect to t, that being the implicit differentiation step right there. And if this goes over your head just a little bit, you're not comfortable with it as you just learned this idea of implicit differentiation, know that that's okay. We have an entire lesson in Unit 4 developed around just simply this skill of being able to do this step. So if this feels a little bit overwhelming, know that there's going to be an entire lesson dedicated to what I just did in Unit 4. But I do want you guys to see this because this is a really interesting thing. Right now you understand that there's a formula that relates the volume of a sphere with its radius. But if you take a look at this equation right here, not only am I relating the radius, think about what dv over dt and dr over dt represent. This represents the rate at which volume changes over time. This is the rate at which radius changes over time. And so this gives us a new perspective, a new formula for the volume of a sphere in terms of how it changes over time. So imagine if I took a spherical balloon and I was inflating it. The volume would be changing over time, and now I have a formula that's going to relate various things with that sphere to the rate at which the volume is changing, or the amount of air maybe I'm inflating into it. So this new equation, and I just think this is one of the neatest things that we get out of calculus, is it gives us a really brand new perspective on so many things we did in geometry. It gives us new concepts. And that is the rate, because remember, that's really what we've been talking about this whole time, is rates of change. So we're looking at the rate at which volume and the radius change with respect to t, or with respect to time. And we're going to build a lot of things in Unit 4 that involve using this implicit differentiation to get some brand new perspectives on a lot of those formulas you learned in geometry, and it's a really exciting topic to get to learn in calculus.